We're going to look at the relationship between exponential functions and logarithmic functions. Recall that exponential functions look like y equal b to the x, where b is greater than 0 and not equal to 1. And I can graph exponential functions for different values of b. I know that if b is bigger than 1, my graph looks like this. This is y equal b to the x. Okay, hang on. Y equal b to the x. This is if b is larger than 1. I can also graph an exponential function if b is less than 1. Looks like this. This is y equal b to the x. Be very careful though when I say less than 1. It's less than 1 but still bigger than 0. So this is true if b is between 0 and 1. It's some sort of fraction or some decimal. Okay? These graphs have a few things in common. Exponential functions have several properties, so let's start writing them out. Let me scroll down just a little bit. So we'll start with properties of exponential functions. Okay. First thing, if you look at both pictures, we can look at the domain. We can get that from our graph. We can also think about an exponential function as y equal b to the x. What x values would cause an issue? Remember, domain means we have to, what x values would make me divide by 0 or have a negative under an even root, things like that. So we see that there will not be an issue. Any x we plug in is going to give us a y output that's okay, that's a real number. So our domain is all real numbers. Remember, or you may say from negative infinity to infinity. Okay? And then what is the range? If you look at your pictures, what y values does this attain? If I continue this graph on forever, will it hit every y value? Remember, the basic idea is to start thinking about this is, will I get positive y values? Yes. Will I hit every positive y value? Yes. Will I ever get y equals 0 for either of these? Does it look like it with the picture? Will y ever be negative? Again, it doesn't look like it with my picture. Okay, so looking at my equation, y equal b to the x, can y ever be 0? Remember, b is some constant, x is a variable. So if x gets larger and larger and larger, and b is bigger than 1, y is getting larger. If x gets small, if x is negative, remember if I have y equal, let's just say 2 to the x, what if I put in 2 to the negative 2? This negative up here for x just makes this a fraction. So again, this is still positive. So if I plug in different x values, I can see that I'm still plugging in, whether they're positive or negative. If I plug in something positive, I still get something positive. If I plug in something negative, even if it's a 2 to the negative 4.63, well, that's just 1 over 2 to the positive 4.63. May not be an integer or a rational number, but it still is positive. So I'm never, ever, ever going to get y to be 0, and I'm never going to get negative y values. So my range is from 0 to infinity, not including 0. Okay, do we see that the graph has some special points? So the graph has a y-intercept where? Well, for both of these, where b is bigger than 1 and b is a fraction, what is the y-intercept? Remember, this is the y-axis. I did not label them. This is the x-axis and the x-axis. So where does the graph cross the y-axis? At the y-intercept. In this case, it's the point 0 what? If we let y equal b to the 0, what is b to the 0? As long as b is not 0, anything to the 0 power is 1. So this is 0, 1, and this point as well is 0, 1. So the graph has a y-intercept at 0, 1. Okay. Do we see that the graph has a horizontal asymptote as well? Do you see it? Where is it? Well, if I look at my graph, I can see that, look at this first one, that if x gets larger and larger and larger, so does y. What happens when x gets smaller and smaller and smaller? If I put in negative numbers, we saw here, I just end up flipping things. So 1 over 2 to the 100 is very small because 2 to the 100 is large. So 1 divided by something large is very small. The y values get more and more and more negative. Same thing over here. In this case, if b is a fraction, and I plug in something, so let's say y is maybe 1/2 to the x, or 2 to the negative x. If I plug in 2 to the negative 1, let's put in a positive 1, I get 1/2. Can we see that? If I put y equal 2 to the negative, let's put in negative 3. Well, that becomes 2 to the positive 3, I get 8. So here, to get the y values closer to 0, x moves further to the right, to the positive values. But in both cases, just like we saw with the domain, y will never, ever, ever cross the x-axis, or the line y equals 0. So the graph has a horizontal asymptote at y equals 0, which is the x-axis. Okay? We see that the graph passes through another point, no matter what b is, passes through the point 1 comma what? If I put in 1, what do I get? If I put in a 1 for x, I get y equal b, right? So this is 1 comma b. So over here as well, 1 and b is, we see here b is between 0 and 1. So 1 comma b. So it passes through the point 1 comma b. Let me scroll down just a little bit. I see that if b is larger than 1, then y equal b to the x is increasing or decreasing? B is larger than 1, it's increasing. What happens if b is a fraction or a decimal? Well, graph is decreasing. Okay, so those are all the properties of the exponential functions depending on cases of b. So now we're going to compare this to logarithms. So I'm going to go ahead and erase my little scratch work here so I can put properties of logarithms. So if I look at logarithmic functions, I want to see what's happening there. Okay, so let's look at what we have. Okay, can you see that both pictures are graphs of a one-to-one function? Is that true? First off, they pass the vertical line test. That means they're a function. But do you see they also pass a horizontal line test? Any horizontal line I draw will pass through the graph only once. So exponential functions are one-to-one. Okay, can we see that? Exponential functions are one-to-one. So they have inverses, right? Okay, do you remember how to find an inverse? Well, we have the function y equal b to the x, then what's the next step? We switch x and y. If we do that, we get x equal b to the y, right? Okay, what else do we know about inverses? We know that if we graph inverses, there's a line of symmetry somewhere, right? Where's the line of symmetry? The line y equal x, so that's beautiful. Oh, okay, got it. That one's off a little bit. I'm really good with this thing. There we go. Maybe not. Okay, so let's pretend that's the line y equal x. We know that if we graph two inverses, that they have symmetry about this. We also know that when we're looking at the equations, we switch the x and y. We switch it when we're solving it algebraically. We also switch the points. Okay, so if I'm going to plot this, let me plot this one, I guess, in a different color. What color can you see? Do it in this blue color. So if this is the point 0, 1, I'm going to plot the point 1, 0 over here. This is the point 1b, I'm going to plot B1 right here. Okay, and I'm just going to kind of graph this so that it looks, you can sort of see that symmetry, and my picture's off a little bit, but you'd be surprised if it wasn't. Okay, so maybe more like that. Is that kind of, can you kind of visualize that? So this would be like the point B, comma 1. Okay, if I fold it over along this red line, these should line up. Okay, let's do the same thing over here. What if I'm going to plot this inverse? Okay, so this is the point 0, 1, so here's the point 1, 0. It's going to kind of go like this, pretend that crosses. Okay, so those are the graphs of the inverses. Okay, so we said that inverse has the equation x equal b to the y. Does that look familiar? Do you remember when we first started talking about logarithms? We said we call log base b of x was equal to y, right? Y equal log base bx. And then to undo a logarithm and write it in its exponential form, we do b to the y equal x. B to the y equal x. So do you see that if we have an exponential function, we switch the x and y, we do get a logarithm? It's just written as an exponential function, but these are equivalent. So this guy right here is y equals log base b of x. Y equals log base b of x. So now let's look at our graph and think about what we know about inverses, and we're going to see if we can come up with similar properties for the logarithms. So I'm going to scroll down a little bit. Okay, if we're talking about domain, we know the domain of a function is the range of its inverse. So I know automatically that these guys can be switched. The domain of an exponential function is going to be the same as the range of a logarithm because they're inverses. So the range is all real numbers, or I can write it like this. The domain will be the domain of a logarithm will be the same as the range of an exponential function, so from 0 to infinity. Now let's look at our pictures again. If I look at this teal one, I see that the domain is numbers larger than 0. It's never going to cross this. Okay, same thing here. Range, but I'm going to hit every single y value. If I continue to do this on forever, I will hit every single y value there is. Okay, now let's look at this next bullet. This one says an exponential function has a y-intercept at 0, 1. Okay, here's the point 0, 1. So what is this point right here? We said we switched the x and y, so that's the point 1, 0. What about this one? Also 1, 0? So guess what this graph has? It has an x-intercept where? At 1, 0. We switch the x and y's. Okay? Now, exponential functions, this blue one, have horizontal asymptotes at y equals 0. Okay, but we flip the x and y. So if this is at y equals 0, guess what this teal one will have? X equals 0. We flip the x and y. So, but it's not going horizontal anymore. Now it's vertical. So the graph has a vertical asymptote at x equals 0, which in this case is the y-axis. Do you see what we did? We're just switching the x's and y's. Now look at your picture. Is that true? That means it will never, ever, 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 ever cross the line x equals 0 or the y-axis. Try it with your calculator. Can you put in log of a negative number? Nope. Can you put in log of 0? Nope. It's never going to cross. Let me scroll down a little bit. And the reason it's never going to cross is log base b of x. if that's equal to y, that's the same as b to the y equal x. There's no y value you can plug in to get x equals 0, just the same as we got over here. Okay, now this graph passes through b comma 1. If this one passes through 1b, this one better pass through b1. Does that make sense? And if b is larger than 1, y equal log base b of x is increasing. Do you see that? If b is between 0 and 1, y equal log base b of x is decreasing. So these last two bullets end up being the same, but look at your picture. See the same relationship? Okay. Isn't that neat? If you understand inverses, this is amazing. This tells you so much. I'm going to scroll down a little bit more. We also have some properties that say if you take b to the log base b of x, what do you get? Do you remember? Anybody? We end up with x. Why is that? Because it's a property, okay? But why else? Okay, recall if f and f inverse are inverses of each other, f composed with f inverse, if I operate that on x, I get x back out, and f inverse composed with f, if that operates on x, we get x back out. Okay? Note, b to the x and log base b of x are inverses, aren't they? This is y equal b to the x, and this is y equal log base b of x, right? B to the y equal x. So, if we compose them, we get the variable we started with. Okay, also, log base b of b to the x is equal to x. So these are the two properties. So let's just check it. I'm just going to kind of arbitrarily assign. Let's say maybe f of x is log base b of x. Maybe f inverse is b to the x. So if I do f composed with f inverse of x, that's the same as f of f inverse of x, which is f of b to the x. That means instead of this x right here, I put b to the x in its place. Log base b of b to the x. And this equals x since these are inverses. I'm going to do the other way. F inverse composed with f. Well, that's f inverse of f of x, which is f inverse of log base b of x, which means log base b of x goes in place of this little x right here. This is b to the log base b of x, which is x, since these are inverses. It's pretty neat, right?